Now we're going to look at rate word problems. We're going to focus on distance, speed, and time problems, and then we're going to look at work rate problems. So the relationship between distance, rate, and time is given as this. Distance is speed or the rate multiplied by the time. And then rate is the distance divided by time. So distance is speed multiplied by time. And then we can deduce the others. We can say speed is distance divided by time, and time is distance divided by speed. Now let's look at some word problems. Two cars started from the same point at 9 a.m. So they are traveling in opposite directions at 20 and 40 miles per hour respectively. At what time will they be 330 miles apart? So let's kind of try to diagram this. So we have a starting point. Let's call this point A. One car goes in this direction, let's say 40 miles per hour. Another car, and the second car goes in this direction at 20 miles per hour. We want to find out at what point will they be 330 miles per hour apart. So let's look at the distance. Distance is given as speed multiplied by time. So there's going to be a consistent time here. So we can say this is car 1 and this is car 2. So for car 1, the car 1 would cover a distance of, let's say car 1 distance is 20 miles per hour multiplied by time, which is t. Car 2's distance is going to be 40 miles per hour times t. So to get the distance apart, we're going to add the distance covered by car 1 and the distance covered by car 2. And at that point, we'll be able to determine how far apart they are. So distance covered by car 1 is 20t. Distance covered by car 2 is 40t, and they are 330 miles apart. So 60t is going to be equal to 330. So we divide by 60 on both sides, and so we have t is going to be 5.5 hours, or we can write this as 5 hours and 30 minutes. Now, we want to understand if this is actually valid. So let's multiply 5.5 by 20. So we have 110 miles this way, and for car 2 you have 220 miles this way. So you can see that this right here is 220, this here is 110. So you can see that this car right here and these two cars are about 330 miles apart. But the question is not done. It's asking at what time. So what we're going to do is we're going to add the number of hours, the duration here, to 9 a.m. so we can know what time it would be, 5.5 hours from when they started. So this is going to be 9 a.m. and then we add 5.5 hours to this. So this is going to give us 1430 hours. And of course, we can convert it since it's in AM PM. So we're going to subtract 12 hours. So it's going to be 2:30 p.m. So at 2:30 p.m., if the cars drive at these speeds, they will be exactly 330 miles apart. So John left home and drove at a rate of 45 miles per hour for 3 hours. He stopped for lunch, then drove for another 3 hours at the rate of 55 miles per hour to reach his destination. How many miles did John drive? So let's look at the first distance he covered. Let's look at first part of his journey. He drove 45 miles per hour. So distance is speed multiplied by time. So 45 miles per hour multiplied by 3 hours. So he drove 135 miles the first time. And then for the second part of his journey, so second part, we also know that distance is speed multiplied by time. Second part, he drove 55 miles per hour for 3 hours, which gives us 165 miles. So how many miles did he drive is going to be the sum of the first part of his journey and the second part of his journey. So total distance is going to give us 135 miles plus 165 miles. When you do this addition, you should get 300 miles. So we're going to look at this rate of work problem. It takes 1.5 hours for John to mow the lawn. Linda can mow the same lawn in 2 hours. How long will it take John and Linda working together to mow the same lawn? So for John, it's 1.5 hours for the lawn. For Linda, it's 2 hours. So what we're trying to do, the first thing we're going to do is, what is John's rate of work? So how much of it can he do in 1 hour? So for John, the whole lawn, so let's do this. One lawn takes 1.5 hours. So we want to find out how much of it he can do in 1 hour. So we're going to have 1 over 1.5 of the lawn. So this is the fraction of the work he can do in an hour. So this is going to give us 2/3 of a lawn per hour. Okay, for Linda, she can get through one lawn or one piece of lawn in 2 hours. So we want to find out her rate of work. So this is amount of work she can do in 1 hour is going to be 1/2 of the piece of lawn. Now we want to find out, if they work together, what is their rate of work. So what we're going to do with that is we're going to add up John's rate, which is 2/3, and Linda's rate, which is 1/2. So when they work together, their rate of work is going to be, let's do the fraction here. So this is going to be lowest common denominator of 6. So this is going to be 6, and this is going to be 4 over 6 plus 3 over 6, which is going to be 7 over 6. So if they work together, they can get through 7/6 of the lawn in 1 hour. So if they can get through 7/6 of the lawn in 1 hour, how long will it take them to get through one piece of the lawn? So 7/6 of a lawn can be done in 1 hour. So the whole lawn is going to be 1 divided by 7 over 6, which is going to be 6/7 of an hour. Now let's look at another example. A tank can be filled by pipe A in 4 hours and by pipe B in 6 hours. When the tank is full, it can be drained by pipe C in 8 hours. If the tank is initially empty and all 3 pipes are open, how many hours will it take to fill up the tank? So let's start with pipe A. Pipe A requires 4 hours. So what is the rate of work? The rate of work for pipe A is, so you have one tank, so 4 hours are required to fill one tank. So in 1 hour, pipe A fills 1/4 of the tank. Let's look at pipe B. Pipe B requires 6 hours to fill 1 tank. And so in 1 hour, pipe B is going to be able to fill up 1/6 of the tank. Now we have pipe C. Pay attention to what pipe C does. Pipe C is a draining pipe, so that's very important to note. So it requires 8 hours to drain 1 tank. And so in 1 hour, it can only drain 1/8 of the tank. So now, when they are all working together, so pipe A plus pipe B, but then pipe C is draining, so it's going to be minus. So we have 1/4 plus 1/6 minus 1/8. This is when they work together. So if they're all working together, this is what you should see for the effort in 1 hour. So let's simplify this. So the least common denominator here is going to be 24. So I'm going to have 6/24 plus 4/24 minus 3/24. So this is going to give us 7/24. So when they work together, 7/24 of the tank can be done in 1 hour. So this is showing us that 7/24 of the tank is filled in 1 hour. So we want to find out how long is it going to take to fill up the tank. So the tank is represented by 1. So 1 tank is going to be 1 divided by 7/24. So it's going to give us 24/7, which is 3/7 hours. So if these 3 pipes are working together, it's going to take 3/7 hours for the tank to be full. And take note, it's also taken into account that we have pipes A and B filling up the tank and pipe C draining the tank. So after 3/7 of an hour, the tank will be completely full with all these pipes working together.